Limit comparison test. So section 11.4. So what does the limit comparison test say? Let a sub n be greater than 0 and b sub n be greater than 0 for all n. A quicker way to write for all n is like this here. You don't have to know that, but just in case you want a shortcut. Now, and what else do we have? The limit as n goes to infinity of a sub n divided by b sub n equal to equal to L, where L is finite and positive. So like L could be like 3, right? If L is equal to 0, that is not a positive number. Okay, that's not a positive number. So we cannot have what? Not infinity and not 0. All right? If this is the case, then both series converge. Okay. Or both series diverge. Okay. So in your text, the book says if L is equal to 0 or L is equal to infinity, then the test is inconclusive. It fails. All right? But I'm going to give you a way to get around this in a sense. All right? This is extra for you. The Clarke Way. Patent pending, right? So the Clarke Way. If the limit as n goes to infinity of a sub n over b sub n equals 0, now that's one thing. And what else? We got to know something else. The series 1 to infinity of b sub n converges, then, so we have to know a little bit more information. Then, what can we say about a sub n? The series n going 1 to infinity of a sub n converges. Okay? Then that series converges. So what is this telling me? All right? Now look. If we have a ratio of an over bn, and we take the limit as n goes to infinity, and the limit is 0, that tells me that bn dominates an. Okay? So let me write that out. So bn has to be larger than an. It's stronger. It's just flat out stronger. It's pulling it down to 0. Okay? Since bn dominates so much that it pulls the limit to 0 as n goes to infinity, what does that tell me about an? An is less dominant, right? And since bn converges, that means an has to converge. Okay? Now, another thing, instead of being, potentially, instead of L being 0, we run into the scenario of if the limit as n goes to infinity of an over bn is equal to infinity, okay? Now, if that's all we know, then the test fails and we're done, right? So if that's all we know. But if I also know and the series n equal 1 to infinity of an diverges, I'm sorry, not an, but bn, diverges, then what's going to be true? N equal 1 to infinity of an also diverges. Okay? So let's think about this for a second. An divided by bn. As n goes to infinity, if I'm going to infinity, this ratio goes to infinity, that means that an dominates bn. Okay? But if I know that an dominates bn, so that means what? That means that an has to be larger than bn. Okay, so that's what we know. An has to be larger than bn as n goes to infinity, right? What does that tell me about an? That tells me that since bn diverges, since that's diverging off to infinity, and an's bigger, then an also has to diverge to infinity. All right, it's forced to. Okay? So you think about the little airplane examples. If I know oh man, that is a pretty airplane, right? My little bn is going off to infinity. Let me copy this because this is such an amazing plane. I want to make two of them, right? And I have my an here. If I know that the bn is going off to infinity, I know that it diverges, and this is going to infinity here, that means that an is dominant. It's more dominant than the bn. So what is the bn going to do? It's going to force the an to go off to infinity with it. Okay? So it forces the divergence here. So just in summary here, if you don't have to worry about these special cases if your answer is some finite positive number, meaning as long as it's not infinity or 0, you're good. Either both converge or both diverge. Okay? But if you get an answer of 0, right? If you get some answer of 0 here, then looking at that problem, okay, it would be inconclusive if all you knew was it was 0, the limit of the ratios, an over bn, of those sequences. But if you also know that bn converges, okay, then by golly, an has to converge also. And same way here. If I have infinity for my answer here, that means my an was dominant. Okay, it was more strong. It was growing faster. But if I know that my bn is already dominant and it's going to go to infinity, but the an's going to infinity even quicker, then an has to diverge as well. Okay? So those are just special cases there, so don't get too hung up on that. This is the main thing that we got to make sure that we know what we're doing. Okay? So let's work through some problems together. We're going to use limit comparison test to show the series converges or diverges. Remember, we're not trying to figure out what the series adds to. All we're trying to do is figure out, did the series converge? Did the series diverge? Okay? So n equal to 1 to infinity, 1 over n plus the square root of n. All right? Now, when I look at this problem here, looks like a big old mess. Okay, it's not a P series. Okay, but perhaps it behaves like one. Okay, so my job is to pick a series that I know something about, right, and then compare it. So one thing that might help you out when you're doing limit comparison test, if you want to write LCT, that's fine. And then direct comparison test, if you want to put DCT, that's fine too. That's just a shortcut for you. Just a little side note. But looking at this sequence here, all right, 1 over n plus square root of n, who's the dominant term here? Well, it's the n. The n is a degree 1 term, okay? So what does that tell me? That tells me that this thing, but a good thing to compare it with might be the series n equal 1 to infinity 1 over n. What do you know about series 1 over n? This is the harmonic. The harmonic series is a P series P equal to 1. This diverges. Okay? We proved that it diverges earlier on. Now, how do I do this? How do I run the limit comparison test? Okay? First, I need to make sure that both of my sequences here are positive, and if n is greater than or equal to 1, then 1 over n plus square root of n, that's definitely greater than or equal to 1. It's positive numbers, right? And then 1 over positive plus positive is still a positive number. We're good to go. And what else do I have? 1 over n is also greater than or equal to 0 too. So we are good. We don't have to worry about being negative terms here. Okay? Now, I take the limit as n goes to infinity of what? Well, it's the an over bn, right? So this is the limit as n goes to infinity of, well, the first one is 1 over n plus the square root of n divided by 1 over n. Okay? This is equal to the limit as n goes to infinity. And then what I'm going to do is I'm going to keep, change, flip. Okay, so what does that mean? Let me move this down here. I keep the numerator the same, 1 over n plus the square root of n. I change division to multiplication, and I do the reciprocal here. And now when I multiply, I get the limit as n goes to infinity of n over n plus the square root of n. Okay, the numerator degree is 1 and the denominator degree is 1. So when the degrees are the same, all right, all we have to do is divide the coefficients. If you wanted to use L'Hopital's, you could, because it's infinity over infinity. L'Hopital's rule tells me that this is equal to 1 over 1 plus, n to the 1/2's derivative would be 1/2 n to the negative 1/2. So that's 1 over 2 square root n. And when I take this limit here, I get 1 over 1 plus, and then this piece right here is going to drop off to 0 as n gets arbitrarily large. And so my limit is 1. This is finite and positive. So that's what I'm looking for, finite and positive. So what does that tell me? Therefore, by the limit comparison test, see how quick that is to write? The series n equal 1 to infinity of 1 over n plus the square root of n diverges since the series n equal 1 to infinity of 1 over n diverges by P series P equal to 1, and the limit as n goes to infinity of 1 over n plus the square root of n divided by 1 over n equals 1, which is finite and positive. So we're just summarizing everything that we did here. So this is what I'm looking for as you write your answer. Tell me what test you're using and then what tests back up those tests, right? Let's do another one. Okay, here's another example. Series n equals 0 to infinity, 4 to the n over 7 to the n plus n squared. Okay, when I look at this, what's throwing me off here? Well, it's this n squared term. This makes it not a p series. And it's also not a, well, if I have a to the n power, that's geometric. So it's not geometric either. So, and then I look at that, I'm like, well, I'm not really sure how in the world I would integrate 4 to the x over 7 to the x plus x squared. That might be a difficult integral, right? So p series, geometric, and I don't see a telescoping. So it kind of leads me to, well, maybe I can compare it to something that it's similar to. What is dominant here? The dominant term in the numerator is 4 to the n. The dominant term in the denominator is 7 to the n. So this is behaving. So I ask myself, what's dominant? Okay. So it's behaving like 4 to the n over 7 to the n for large n, which this is the same as 4 over 7 all raised to the n. And that looks like a geometric. Okay, so what I'm going to do is I'm going to compare with n equals 0 to infinity of 4 over 7 to the n, a geometric series with a, remember a is your first term, so if I plug a 0 in, I get 4/7 to the 0, which is 1. And a geometric ratio equal to 4 over 7. Okay, what I multiply each term in the sequence by to get the next term. And since the absolute value of r, which equals 4/7, is less than 1, what does that tell me? The series 4 over 7 to the n equal 0 to infinity, converges. Now remember, I don't care what this thing adds to. All I want to know is, does it converge or diverge? So if I'm going to compare this with this here, and I know that this one converges, and I get some limit that's finite and positive, then I know that the other series is going to converge as well. Okay? So let's work out a comparison, see what happens. So let's take 4 to the n over 7 to the n plus n squared. This is definitely greater than 0 for n greater than or equal to 0. And we also know 4 over 7 to the n is greater than 0 for n greater than or equal to 0. Okay? So let's run our limit comparison test. Limit as n goes to infinity of what? 4 to the n over 7 to the n plus n squared divided by 4 to the n over 7 to the n. Okay, so let's see if we can't figure this out. Keep, change, flip. So I'm going to keep the numerator the same. 4 to the n over 7 to the n plus n squared. Change division to multiplication, and then flip the denominator 7 to the n over 4 to the n. Okay? Cancel, cancel. So what do I get? What do I get here? I get the limit as n goes to infinity of 7 to the n over 7 to the n plus n squared. Now, when I look at this, looks like it behaves very similar in the numerator and the denominator as n goes to infinity. So I'm thinking that this limit's going to be 1, but I can use a little bit of algebra here. Okay, if I use a little bit of algebra, I can factor out the 7 to the n in the numerator and the denominator and cancel. And so I get 1 over 1 plus n squared over 7 to the n. Okay, y'all see what happened there? Look, I can factor a 7 to the n out, and that leaves me a 1 plus n squared over 7 to the n. Okay, and then the 7 to the n's cancel each other. All right, so now when I take the limit, I get 1 over 1 plus, well, who's going to dominate here? The 7 to the n is growing faster than the n squared, so this term goes to 0 as n goes to infinity. And so I get 1, which is finite and positive. So what does that tell me? That tells me that what we're going to do is have this series also be convergent. Why? Because the series that we compared with is convergent. So let's write this up formally. Therefore, by the limit comparison test, the series n equals 0 to infinity, 4 to the n over 7 to the n plus n squared converges. Since, well, why does it converge? Okay, well, it converges because series n equals 0 to infinity of 4 divided by 7 to the n converges. Geometric, a equal to 1, r equal to 4/7. Absolute value of r less than 1. Okay, so we know that to be true. So that tells me it's geometric and it converges. All right, since this is true and the limit as n goes to infinity of 4 to the n over 7 to the n plus n squared divided by 4 to the n over 7 to the n is equal to 1, which is finite and positive. Okay? All right. So hopefully that helps you out a little bit. Now I want to do one more problem, and this one will hopefully illustrate for us the little trick that we had in the Clarke Way. And so let's go to it. Series n equal 1 to infinity, ln n over n squared. Ln n over n squared. This one's a tricky one, okay? When I look at this, I'm thinking, maybe it converges, maybe it doesn't converge. If I have n squared in the denominator, well, look, I know, like, comparing it with, like, I don't know, 1 over n squared. Look, I know that this thing converges. This converges. P equal to 2. P series P equal to 2. So if I take the limit here, okay, limit as n goes to infinity. Now let's do ln n over n squared divided by 1 over n squared. Simplify here. Limit as n goes to infinity of ln n over n squared times n squared over 1. So I get the limit as n goes to infinity of ln n. Well, this is equal to infinity. Okay? Now, the test fails here. Test fails. Why did the test fail here? Why did it not work? Look, I compared it with something that I knew converges. But whenever I took the limit what did the limit tell me? The limit told me that it was infinity here. So what did that do? If it's infinity, that means the numerator is dominating the denominator, right? So this just really was a little bit too much, okay? A little bit too much here. So maybe let's try, and why can't we use our infinity here? So the little Clarke trick said, okay, if I know Bn diverges, so in the denominator diverges and I get infinity, then that tells me something about An. But look at this. I don't know that diverges. This actually converges, so that doesn't work there. We can't use the trick Clarke Way there. So let's try it. Maybe this one was going down to 0 too fast. Maybe this thing behaves like, more closer to like 1 over n maybe. So let's try that. So let's compare with series 1 over n. Well, what do we know about this one? Series 1 over n, this is a divergent. P equal to 1. Okay, P series, P equal to 1, this diverges. Okay, when I run the test, the limit as n goes to infinity, because look, if I can get infinity here, and I know that the bottom diverges, then that means the top is going to also diverge, right? So that's what our goal is. So let's try it, because now I've picked one where it does diverge. So let's try it again. So ln n over n divided by 1 over n. Okay. So when I do my simplification, limit n goes to infinity, ln n over n squared times keep change flip ln n over n. How do I do this? I do L'Hopital's rule. Take the derivative of the numerator. Derivative of ln n is 1 over n. Derivative of the denominator, derivative of n is just 1. And when I type this, whenever I plug in infinity, I get 0 over 1, which is 0. Well, dadgummit, the test fails again. So I went from one end of the spectrum to the other. Okay, I went from going and getting infinity to getting 0. This helps us none, because remember, if I know that the series converges, if the denominator series, if that thing converges and I go to 0, that means that this is more dominant, and therefore this one has to converge if the more dominant one converges. But this is not the scenario. I have something that is super dominant. Okay, it's more dominant in the denominator, but it diverges. So that means that the top could converge, it could diverge. So we went too far with n squared, and we went too far back the other way with just n. So maybe there's something in between n squared and n that might work. So maybe try series 1 over n to the 3 halves, 1.5, right? We're getting kind of wonky here. Okay, so what do we know about this? This is a p equal to 3 halves, which is greater than 1. Therefore, this converges. Okay, p series. Now, if it converges, okay, and it's in our denominator, then I want it to be going to infinity, right? And then if it goes to infinity, then hopefully, if it goes to 0, then hopefully we'll be finished, right? Because if we know that the series converges what we're comparing with, let's look here. So if we know that the series we're comparing with converges and the limit goes to 0, then we know that numerator one converges. That's the Clarke Way, right? So we're trying to see, does the limit equal 0? Okay. So let's try it. So limit as n goes to infinity of ln n over n squared divided by 1 over n to the 3 halves. Simplify here, keep change flip. We get ln n over, looks like it's going to be the square root of n. Okay. I can use L'Hopital's rule here, take the derivative of the numerator and the denominator. What do I get? I get 1 over n divided by, 1 over 2 root n. Okay. Keep change flip. I have 2 over the square root of n. Right? Okay, and so this is going to end up giving me 0. Now, since the series n equal 1 to infinity 1 over n to the 3 halves converges by p series p equal to 3 halves, and the limit as n goes to infinity of ln n divided by n squared divided by 1 over 3 or n to the 3 halves is equal to 0, then by Clarke Way, CLT, I'm sorry, not CLT, limit comparison test. Sorry, I was thinking statistics there. LCT. Okay. What does that tell me? That tells me the series n equal 1 to infinity of ln n over n squared also converges. Okay. So good luck trying to work through that problem right there. Okay. All right, guys.